And I'll start from the slide where we stopped yesterday. So yesterday we were talking about the data assimilation. We said that the two major components of the data assimilation is the model and the analysis scheme, right? And we were discussing about the cycling yesterday. So is the cycling part clear to all of you? Do you understand what is the cycling? Now you already there on the screen.
Yes, sir.
Okay, so anyway, we were saying that there are two modes there can be. One is the cold start and other is the cycling part or hot start, you can say. Cold starts take place when you are starting for the first time and you have no past history of your analysis. So that is the cold start. Whereas when you're doing the continuous assimilation or analysis, then there is a cycling part, because every time you make a forecast for 6 hours, and that forecast becomes the first case for that 6th hour where you have got the new observation, right? So that we discussed yesterday. Now, continuing that, let's talk about something about the data. We have already discussed many times about the data issue, because data is a backbone of any NWP. So once again, we shall try to discuss about the data. Okay. As you know, the observations data received in coded form are to be deciphered and subjected to checks to eliminate errors due to instruments, communication, and transcription. Right? We have discussed this in the data processing and quality control lectures in the beginning, right? And we also have discussed that every data is shared or communicated in a coded form, which is the standard format defined by the WMO. Right? So this coded data has to be decoded first of all. Right? It has to be deciphered, and then after that we do all sorts of checks to eliminate the errors like instrumental error, communication error, transmission errors, etc. The decoders are used to convert the data to convert all data into a common format such as buffer. Buffer stands for binary universal form representation of meteorological data. So this is a very uh, common format of the data which is used to share observations between different countries, and is set by the WMO buffer format. Okay, we have got other formats also like grid. You have heard about the grid, right? Grid format, buffer format, and what else? NetCDF also you have heard about. Okay, HDF. So there are different formats for coding the meteorological data. Okay, and sharing with each other. The raw observations are checked for instrument errors before they get into the data stream that you know. Then the data are checked for gross errors, physically impossible values, right? That's what is the gross error that we have discussed in the beginning classes, the data processing. And also the duplications. Now, sometimes there are duplicate data that has to be also checked and eliminated. Okay. Similarly, biases in observations are also identified, such as biases in the humidity that differ with manufacturing agency. Okay, biases in ACARS. ACARS is the aircraft data that we have talked about earlier. ACARS stands for Aircraft Communications Addressing and Reporting System data. Do you remember what are the other formats of the aircraft data? Can somebody tell what is the other format of aircraft data? You don't remember? Are you able to hear me?
Yes, sir. I don't
Okay.
remember.
Yeah.
Even me.
So, do you remember the another format of the aircraft data format? Probably don't remember. Other is a AMDAR. Okay, AMDAR. Yet another format is a ARIPS, AIR, REPS, aircraft report. So there are three formats used to transmit the aircraft observations: ACARS, AMDAR, and ARIPS. Okay, that all those things you should remember, because sometimes you have a small objective questions on these things. So yesterday we discussed about this diagram, right? Remember this diagram yesterday we discussed? Let me also
Yes, sir.
start using the laser pointer, right? And to just review once again, what we said was that now this blue line represents the observation. Okay, this is your time and this is your space x, the x space. So I got observations distributed in a space. Okay, coming at different times. We also talked about the data cut-up time or time window, etc., assimilation window, etc. So these are the data which are available at different locations in space represented by the blue line. Okay, and we have said that always in a data assimilation system or in objective analysis scheme, you use a first guess at all the grid points of the model based upon the previous 6-hour forecast. So let us say this green line is your first guess, okay, from the previous 6-hour forecast. Now, because this forecasts are not accurate, even after 6 hours, it may not be perfect. So this has to be corrected, okay, or it has to be brought close to the observation, which is this one. So the aim of the objective analysis scheme and data assimilation scheme, of course, is to bring this green line close to the blue line, okay. And let us say this red line represents your analysis. After you have done the analysis, then this is the red line, right? Now, what you notice in this is that in this part and in this part, the red line is closer to the blue line. But in this part, the red line is far away from the blue line. And this is because wherever there is a data observation, new observation, you're trying to correct your first guess. But where there is no data, your first guess cannot be corrected. So your new analysis is same as the first guess, almost same as the first guess. There will be some minor differences because depending upon your radius of scan, we talked about the radius of scan yesterday, day before yesterday. Depending on how far away from your grid point of interest you are considering the observation radius of scan, and also the distance between the grid point and the observation location, all those things. So now this red line will not be exactly same as the green line even in the data sparse region, because you are considering the impact of the data which are far away also, right? So this is what is the concept of the data assimilation: to correct your forecast based upon the new observation and get it as close to truth as possible. Okay. So even after the checks for errors and biases, some of the observations may still have small to moderate errors, which may not be compatible with other observations or the first case fill. These data are subject to quality control checks of the data assimilation system and also manually. See, one is of course done by the machine. Everything nowadays is automatized. But no, even after that, sometimes machine cannot do everything, right? Machine also has limitation. Machine will do only as much as you tell the machine to do, or how much training you have done to the machine, how much the machine is trained. Only that much machine will be able to do. So even after that, there are certain things which people have to check manually. And I was telling you, I think 2 days ago that, for example, in CMWF, they have a big operational forecast from that many places they have, in which they try to check. I mean, there are a set of meteorologists which are assigned the job to check the data quality manually also. Okay. The quality control process of data assimilation system has buddy checks and complex quality control (CQC) that you have studied earlier to ensure consistency between variables and in the vertical profile of a variable, both horizontally as well as vertically. You try to check the data. So buddy checks. Do you remember the buddy checks we discussed earlier?
Yes, sir.
Yes,
Yeah,
sir.
good. Yeah, good. Very good. Can somebody explain what is the buddy check?
So we check the values with our neighbors.
Yes,
Neighbor
we
values.
check the value with the neighborhood check. Like there cannot be a drastic difference between the two neighboring points. Example, there should not be so much of difference between, say, the observation of uh, Ajmer and Kishangarh, right? As an example. Okay, so that is the body check. Now let's see how many methods are there for data assimilation. We discussed many methods for the objective analysis earlier. Okay, similarly, there are many ways of assimilating the data or observation. One category is called the empirical methods. Empirical methods, which include successive correction method that you have heard, in the objective analysis also. Successive correction, that means it is an iteration procedure. You make corrections successively, okay, to the first guess. Other is the nudging. Now, what is nudging? See, by literal meaning of nudging is that you're trying to nudge something close to know a certain thing. Like you're trying to nudge the first guess or the background field close to the observation. Right? And nudging is done not only for the forward time steps or for the future time steps, but it can be done also for the past time steps. Okay, nudging. And there is a weighting factor because that again, three types of nudging: Newtonian nudging, non-Newtonian nudging, etc. So when you say nudging, you are doing the nudging, especially people do nudging in the research mode, not in the real-time forecasting mode. When you're doing the research or doing some experiment, then you do the nudging. For example, if you're starting the data assimilation or impact of the data, you're trying to study the impact of the data. Let us say, okay, say for example, you have collected some new data which is not available in the data bank store. I mentioned you that there is a data bank in NWP centers in which all the data which comes from all over the globe are stored. Yeah, observation store or data bank. But suppose if we have a new observation, like if we have a new AWS installed in our campus, suppose in the university campus, we buy a new AWS and put into the campus, or you buy your personal interest, you buy a observatory in AWS and put into your rooftop of your house, and you want to see the impact of that observation into the model. Okay, so that is a new observation which is not available in the data bank. So for that, what will you do is, suppose if you are trying to study the impact of your new AWS data onto the model. And if there is suppose a thunderstorm, in the campus, in the university campus, there is a thunderstorm. Okay, and you have the data for continuous data from your personal observatory for last 2-3 days, or even more than that. What will you do that? You will collect the data of your past 3 days or 4 days or 5 days that you already have, that is your personal data or personal data, private data of the department, university. Then you will, and suppose thunderstorm occurred today. Generally, that thunderstorms are not predictable for a long time, right? Because it has a very short lifetime span, right? Time scale of the typical cumulus cloud is how much? What is the time scale of a typical cumulus cloud?
1 hour.
1 hour. Yeah, 1 hour is the typical time scale of the cumulus cloud. So you know that we cannot accurately predict the thunderstorm beyond certain time limit. We do nowcasting, say maybe up to say 24 hours you can do fine, but after that errors start going. Okay. So suppose thunderstorm occurred today and you would like to see the impact of your personal data on to the model in forecasting today's thunderstorm. So you may like to start the assimilation based upon yesterday's data, so that you will have at least 24 hours of assimilation from yesterday, or maybe you'd like to make a 24-hour forecast based upon yesterday's data, now valid for today when the thunderstorm actually occurred. Then you may like to start your assimilation from day before yesterday, 2 days ago, right? Because you have the data available with you for last, say, 1 week or so, because that is your personal data, maybe even more than that. So you may like to start from day -2, the assimilation. Okay, and integrate the model from day -2 to day -1, that is for 24 hours. And during that 24-hour period, whatever data you have collected, 6 hours, 3 hours, whatever, you try to assimilate in the model. Okay, that is the past data, day -2. Then similarly, after you have integrated the model from day -2 to day -1, you further input the new data of day -1 into the model, and again integrate from day -1 to day 0. Okay, day 0. So that you assimilated the data from past 2 days, day -2 to day -1, day -1 to 0, and after that you march forward to day +1, then day +2, etc. So by doing so, in the past 2 days, we have just tried to nudge your model close to the observation of the past 2 days. That is the nudging. Okay? You're trying to nudge, make or bring the model close to the reality. Right? Bringing the model close to the reality. That is the nudging. All right. Then there are physical initialization, latent heat nudging. Now, physical initialization, क्या है? It's also very fascinating topic, physical initialization. And this concept was actually proposed for the first time by Professor T.N. Krishnamurti. I've talked about him many times earlier. You've heard of him, right? Professor T.N. Krishnamurti, Florida State University.
Yes.
Right. So this concept was actually proposed by Professor T.N. Krishnamurti. And he had a kind of innovative idea. Because we have generally all the conventional observation, right? Conventional observation means the observation of wind field, observation of temperature field, observation of humidity field, etc. Right? That's what we try to assimilate in the model, because we do the assimilation only generally for those variables which have a prognostic equation, right? This data assimilation that we do is for those data which have a prognostic equation, like wind field, right? A wind field has a prognostic equation, right? Like momentum equations, del u by del t, right? Plus u delta u by del x plus u delta y by del y, and so on. Momentum equation, you remember that? Similarly, you have got the prognostic equation for the V wind, that is the meridional wind, right? V component. You have the prognostic equation for temperature, right? Del T by del T from the thermodynamic equation, right? You have a prognostic equation for the specific humidity also, right? Del Q by del T based upon the moisture continuity equation. Do you remember that?
Yes, sir.
Yes. So generally, we do the data assimilation only for those variables which have a prognostic equation. And they are the conventional observations like U field, V field, temperature field, moisture field. But we also know that beside these standard variables, there are many, many more variables which are observed by so many types of instruments that are existing today, right? And as an example, one of the most common variable data which is available is the rainfall, right? We measure rainfall every day. And rain gauges are available so much in abundance. Thousands of rain gauges are available in India itself, several thousand. Right? Rain gauge, the number of rain gauge stations in India or in any other country, maybe many more times the other observatories the conventional observatory, for example, uh, the one which has a temperature measurement capacity, like where there is a AWS, where there is a Stephenson's screen, they are the standard meteorological observatories. But even where there is no standard meteorological observatory, there can be a rain gauge station because that costs nothing, hardly a few thousand rupees and hardly any space, right? So rain gauges are available in abundance everywhere, in almost all the countries. If the standard observatories are hardly, suppose, for example, take a case of Nepal. Now, Nepal has about nowadays, about 20 to 30 standard stations. Earlier, it was even less than that, synoptic observatories. But nowadays, they have got more number of AWS, automatic weather stations. So altogether, if I count for Nepal, for example, they may have about 20, 30 surface observatories. But if you count the rain gauge stations in Nepal, there will be at least 300, 400 stations because that costs nothing and there is a small instrument. That's it. But of course, nowadays the thing is that those manual rain gauges are not always used. We use the ARG, right? ARG is the automatic rain gauge because who will go and take the observer manually? So then people try to take install the ARGs. So ARGs and manual rain gauge plus the rainfall measurement from the AWS altogether become thousands. And not only these kind of stations which are controlled directly by the India Met Department IMD, but there are many states departments also which also own or possess many meteorological observatories. Like in India, for example, there is ICAR. You have heard of ICAR? ICAR,
Yes.
ICAR,
Yes, sir.
Indian Council for Agricultural Research. Right?
Research.
And there are many agricultural universities also in India. So ICAR has a network of its own agricultural meteorological stations all over India. And whenever there is agricultural meteorological station, they have local data. They have to have. So these stations also have their own rain gauge, and they collect rainfall for the agriculture purpose. And there are many other units like civil engineering dams. Now, where there is a dam, there is a rain gauge station for sure because they like to measure the rainfall. So that water level, they would like to know whether the water level will increase or decrease. Things like that. So I'm trying to say that so much of rain gauge observations, rainfall observations are available all over the world. But are we using those rain gauge observations in the model? Generally, we don't. And so Professor T.N. Krishnamurthy proposed that why not we utilize this rain gauge observation, rainfall observation in the model? Also estimate the rainfall. But how to estimate the rainfall? Question is how to estimate the rainfall because rainfall is not a prognostic variable, right? So he got an idea. Okay, if so, then let us invert it. And I was telling you one day that to have say 2 centimeter of rainfall, then it requires certain amount of water vapor to condense, right? And when there is a condensation of water vapor, there will be a latent heating, right? Latent heating. So that latent heating will feed into the convection, cumulus parameterization. And see how they are connecting physically. They are trying to connect physically. Through rainfall, in order to have the rainfall, there has to be condensation. If there is a condensation, there will be latent heat release. And if there is a latent heat release, there will be an enhancement of the convection. And all these things you are taking into account in the cumulus parameterization scheme. And if you remember, now one of the goal of the cumulus parameterization scheme is also to calculate the convective rainfall, right? Do you remember what are the other two goals of the cumulus convection scheme? Tell me. I told you the three main objectives of the cumulus parameterization.
Convective moisture and convective warming.
Yes, convective warming or cooling and convective drying or moistening, right? So there are the two, and plus the convective rainfall. There are the three. So there are three main goals of the cumulus parameterization, right? So that means cumulus convection scheme has already got a physical relationship between rainfall and then through that to the latent heating, okay, and through that to the convection. So what Professor Krishnamurthy suggested that let us utilize this and invert, like if there is rainfall observation. So for that much of rainfall, how much latent heating would have occurred, right, in the atmosphere, which would have heated the atmosphere. So he tried to develop a inverse cumulus parameterization scheme, right? And from the inverse cumulus parameterization scheme, from the given amount of rainfall observation which is available abundantly everywhere, he tried to invert the latent heating, and that he put into the model. And this way of utilizing the rainfall observation in the model is called the physical initialization, because you are using a physical process, a real physical process, to utilize the rainfall observation, inverting it into the model. Okay, this became very popular, and he demonstrated that by doing the physical initialization, the quality of the forecasts do improve, because again your data and model has improved. Basically, all this idea is to improve the accuracy of your model forecast or solution or product. Okay, by improving the initial condition or by improving the model physics itself, etc. So this is the physical initialization, or called the latent heat nudging. Okay, but somehow because it, again. Since it is not a directly observed, directly prognostic variable, and also is a complex process, because all the cumulus parameterization you cannot really invert. He said that we make a inverse cumulus parameterization, but actually inverse of the cumulus parameterization scheme is easily said than being done, right? Because you have seen all kinds of complex equations in the cumulus parameterization, right? So only the simple type of cumulus parameterization schemes can be inverted, not the complex one. For example, you can easily invert the co-type cumulus parameterization scheme, but not so easily in the Arkawa-Stewart scheme, right? Because Arkawa-Stewart scheme, if you remember, so many equations and complications in that, because that cloud interaction, there is a cloud ensemble model, there is a cloud large scale environmental feedback, quasi-equilibrium systems, so many things are there. Simplex algorithm, Fredholm integral equation of the second kind, operational reservoir, and so many things are there in the Arkawa-Stewart scheme, which makes it more physically sound, but also complicated. So it's difficult to invert the Arkawa-Stewart scheme. And actually, because of its sound physical basis, is so appealing, so fascinating, that people started simplifying the Arkawa-Stewart scheme, and we discussed about the simplified Arkawa-Stewart scheme, the relaxed Arkawa-Stewart scheme, the economic Arkawa-Stewart scheme in the earlier lectures, right? So all these cumulus parameterization schemes based upon Arkawa-Stewart, whether it's simplified or relaxed or economic or whatever, even the Grail's scheme, which is there in the model, those schemes are difficult to invert; they cannot be inverted. So therefore, somehow, although this was a very good proposal of physical initialization, but it was not again used operationally. Only for the research purpose you can do that, but not for the operational purpose. People generally don't do that. Okay, so these are the nudging physical initialization method of empirical data assimilation. Then another category of data assimilation scheme is the constant statistical method, in which we have got the so-called optimal interpolation that we have already discussed today for yesterday's class. This is basically purely a statistical method. Right? We try to compute the observational error, analysis error, forecast error. So many correlations between errors, analysis error, observation error, covariance matrix, and so many things. Right? So they are the statistical method of assimilation. Then there is this next is more improved version called 3D bar, the three-dimensional variational data assimilation. Then Yet another version, higher version is the 4-dimensional variational data assimilation, 4D VAR. So I'll discuss all these things in detail. Yet a third category is called the adaptive statistical method, and which again is slightly more complex, which uses the extended Kalman filtering, all kinds of statistical approaches. Then there is yet another one, ensemble Kalman filtering, ENKF, okay, data assimilation. So there are different ways of data assimilation. So if we represent it now in a flow diagram, then typically in a 6 hours cycle, analysis cycle of the global model, and we have discussed, we have a set of observation at a given time, and we have a background fill for that time. Okay. Then from the observation and the background fill or first guess, you make a analysis, right? Make an analysis, which is supposed to be your closest to the observation, or you regard this as a truth analysis. Then from the analysis, you make a good initial condition. Your analysis is basically initial condition. Okay. And then from that initial condition, then you run the model to get a forecast, a forecast model, right? So from the forecast model, again, you make 6 hour forecast for the next cycle of assimilation, or if you have already made 4 cycles or more cycles of assimilation, then you make a suite of long forecasts, like medium range forecast, right? So from the forecast model, you make operational forecast for, let us say, about 10 days, or from that part of the 10-day forecast, you have got a 6 hour forecast, which again goes back to become the first guess for the next assimilation cycle. Clear? So this is, in a nutshell, a summary of the data assimilation cycle. Okay, 6 hour global data assimilation cycle. All right, 6 hour forecast. Now let's talk about different types of assimilations that we mentioned earlier. That one is the sequential assimilation, in which only the observations made in the past until the time of analysis, that is the current time, are used, which is the case of real-time assimilation system, right? We have already discussed. The next category is called the non-sequential or retrospective assimilation. Okay, that means observations from the future can be used, for instance, in a re-analysis exercise. When you do the re-analysis, of course, re-analysis, like you're doing analysis for many years. Like we started the NCAR and NCEP re-analysis was started from 1979 onwards. Even ERA also started from the 1979 onwards, and recent NCEP out of with regional analysis also from 1979 onwards. But those European centers and NCEP, etc., they have even extended back to 1950s, the re-analysis. So in this case, this is retrospective assimilation, right? Then there is an intermittent or continuous data assimilation, which is assimilation methods can also be classified as intermittent or continuous in time. In an intermittent method, observations can be processed in a small batches, which is usually technically convenient. In a continuous method, observation batches over longer periods are considered, and the corrections to the analyzed state is smooth in time, which is physically more realistic. Okay, we shall see it again in graphical form. Now this graphics represents or indicates or illustrates the sequential intermittent assimilation. Like you have got a set of observations from the assimilation window, plus minus 3 hours, as we said, right? And that you analyzed based upon the first guess for that time, and then make a forecast, 6 hours forecast from the previous cycle, analysis, and then use the model, make the next forecast again at new time. After 6 hours, you have got new observations, again analyze them, okay, again make 6 hour forecast, again you have got new observations, and so marching forward. Right? This is the sequential intermittent assimilation. right? Every time you initialize the model here and make a 6-hour forecast. Here also again you initialize the model, make a 6-hour forecast. So intermittently you are injecting the observation in the model and assimilating it and making the forecast. Now, what is continuous assimilation? In the sequential continuous assimilation, what you are doing is you have got the observations at every 6 hours or so, right? But what you do is when you are integrating the model, suppose from the previous time, say -6 hours or so, then once you reach here at this observation time, instead of reinitializing the model based on the new analysis here, you just correct this forecast, 6-hour forecast based on the new observation, and march forward. Okay, you're not making like a cold start. Actually, in this case, every time step is like cold start here. Whereas you are continuing the integration of the model again for the next time where your observations are available. Again, you correct the forecast there, again march forward. So it is a continuous rather than intermittent. Intermittently injecting the data or continuously using the data. Suppose it is slightly better than compared to this one. Right. Further, you have non-sequential intermittent assimilation. Non-sequential. So in this case, actually, you are trying to fit the entire gimmick or game of the data assimilation is that you're trying to fit the observation into your model forecast so that your model forecast is close to the reality. That's what is the whole game. So in the non-sequential intermittent simulation, rather than merging always forward, going backward and forward, backward and forward. Right? And similarly here, in the non-sequential continuous simulation, you have got a much better, nice, smooth forecast from the model in which you have continuously injected the data whenever they were available. So people also say that in the continuous assimilation, because in the intermittent assimilation, what you are doing is you are injecting the data only at the interval of 3 hours or 6 hours, then 12 hours, then 18 hours, and so on. However, the data is available continuously because many types of data, radar data, satellite data can come in between also. So instead of waiting for the next simulation cycle, as and when the data is coming, you process it, quality control it, and put the model, right? Without waiting for the next cycle to come. So that your forecast times reach is a nice smooth line rather than a zigzag line like this. Right? This is a zigzag line. This is a continuous smooth line. So this is what is the philosophy behind this sequential, non-sequential, intermittent, continuous assimilation cycle. Okay. So let me see how much time I have taken. I thought that now in first 1 hour I'll try to complete this part. So I want it's 12:20. I'll try to finish the 3D bar possible in the next 20 minutes. Do you want to start 3D bar now, or you want to discuss practical? Now you tell me. 3D bar may take about 15-20 minutes time. Let me see how many slides we have got in 3D bar. We are here. And before we reach 4D bar, start from here. So slide number 14 to about 23 or 10 slides are there. So all it will take time. 10 minutes is not sufficient for discussing the 3D bar. Are you able to hear me? Am I audible?
Yes, sir.
Okay. So I think better to start in 3D bar in the next class, and probably it might take half an hour to 1 hour to complete 3D bar. So maybe in next class we shall finish 3D bar, and then we shall take up the 4D bar and go on. Okay. So another, I think, 3-4 lectures to complete all data assimilation. Okay, uh, and that is almost at the end of your syllabus of the NWP theory part. So we can start discussing practical. Is that okay? Yes or no?
Yes, sir.
Okay. So let me first stop recording for the theory part. Otherwise, it becomes a long video, and some people have difficulty in the long videos. So Najmeen has got the